Okay, let's get started. Got a couple announcements. First of all, regarding the, what do you call it, the study guide? Yeah, there was no, the bookstore wasn't able to find any at a decent rate. So what it amounts to is you're kind of all up on, you're all on your own. I thought we could get a good price through the bookstore, and we can't. So if you want, you can go to, to one of the booksellers online and get one, but we're not going to do it as a group. Yeah.
For some other classes, they leave books like that, like in the chemistry help room or the biology room or whatever. Could you make a copy available for us like that? Like just leave one in there that always has to stay in there?
Yes. You're talking about the math study room way down in...
Yeah.
And for math, it's basically in the back, in that corner.
On the first floor or the second floor?
On this floor. Yeah, the math floor is kind of this floor, even though it varies a little bit. But back hall, in that corner of the building, there's a math study room similar to the ones for science.
So there will be a copy of...
Well, I got to take care of it.
Okay.
I'm going to have to order one for us.
I was wondering if that was possible.
Yeah, it's a good idea. I appreciate you bringing it up. It's a good idea. Here's another one from the bookstore. September 12th is going to be, I guess that's when they're sending all the books back. So if you're going to get a book, make sure you do it by then. Let's see, other quick ones here. We've got a few people who I haven't gotten the information assignment from, and some of them are because they're brand new people. I sent out an email to them today. Okay? There are about 5 of you. Other than that, it's worked out quite well. We've got a lot of good response. So if you could, send me that email. And just to remind you, I sent it at least to what I believe is your WLC address. First name dot last name at wlc.edu. Okay, well, we're at 9.4 today. I'm just sorry, P.4, or whatever it's called, P-4. Yeah, P.4. Last time we had P3, and let's start with questions on P3. Yes, Heidi. 65. Okay, let's see. I happen to have that one. If you want me to redo it, I will. Okay, let's see what we got here. Yeah, now this is based on, actually, let's see. I copied it the way it was. Yeah, let me explain what I did. I don't know how many of you remember this. Let me put this, I'm going to just start a new page and I'll come back here in just a second. How many of you remember this? That when you take a plus b times a minus b, I guess that's really the topic for today. You get the difference of two squares. What happens is the two middle terms drop. Why? Because there's a plus ab and a minus ab, and they annihilate each other. Well, if you remember that, then you'll see what I'm doing here. See, this is kind of like this guy plus n times this guy minus n. Those are really conjugates. By the way, we have a name for that. They're called conjugates. And when you multiply conjugates, you get the difference of two squares. That is, you get the first guy squared minus the second guy squared. And then I went through the mechanics of actually squaring each one. What were the directions on this one? I got to make sure. 65. Multiply or find the product. Yeah, I guess we're done then. I thought maybe they wanted to be refactors, whatever. Anybody have follow-up to that? Or Heidi, is that what you were hoping to see? Okay, another one? Yes. 73. Just happen to have that one too. Okay, again, is it the same directions? No, yeah, I guess just multiply it up. Okay, now, The problem is, there is no shortcut for cubing something. You know, I wish you could just take the first term and cube it, minus the second term cubed, and be done with it and smile. There's only one problem with that, it doesn't work. So what I did is I first squared it. I hammered it out using hand shaping, and I got this. And then I just manually did it a third time, multiplied by 2x minus y again. You don't have to bring your like terms. This is, by the way, one way to bring like terms together. You don't have to do that. I'm trying to figure out what I did down below here. This is just, I'm not sure what that is. I guess that's a different kind of two-row multiplication. I was taking 4x squared times negative y plus this whole thing times 2x. I see it now. Anyway, end result after bringing like terms together should look something like this. Yeah. Am I not answering your question?
No, it's back.
Okay. Somebody else or another question. Heidi. 101? Wow, you guys so far have hit all the ones I had. 101. The exercise is 101 and 102. Find a polynomial that represents the total number of square feet for the floor plan shown. Okay, so what I did is just converted this into length times width. 22 was kind of like the width, and the length was 14 plus 2x. And then go ahead and do the length times width. And I wrote it as 308 plus 44x square feet. We can't do any better than that because we don't know what x is. So keep the label, but if you're wondering why there's still an x in there, I don't believe they ever gave us a clue about what x actually is, so we can't do any better. Others from P3. Yes? That's 20. Okay, this is, I have to use the distributive property, so I took 22 times 14, and then 22 times 2x. Good old distributive property. Yeah. Yes? 97. And that's Ben, right? Okay, 97. Just happened to be questions that people asked me before. Okay, if you're wondering, no, did I do them all? No, I did not. So far, just amazingly, everyone you've asked about I've done previously. Okay, so we have this box, and they have kind of the floor plan drawn out for us. Find the volume, and the x. Do you understand that the x is the part that's like folded up to give you the height? Okay, so here is the drawing, and what I did is I added, oh no, they had that in there. So how do you find the volume of a rectangular box? It's basically the area of the base times the height, or if you will, length times width times height. So what I did first is I said, well, what's the base? What's the bottom of this box? Right here. Length times width. And then multiply it by the height. X. That should give us the volume. So I hammered this out, got this, and then I multiplied by x. That gave me this polynomial, and then I think the book said, hey, what are the answers if x is 1, x is 2, and x is 3? I didn't actually do that, but all you'd have to do now is take your polynomial, plug in a 1, see what it comes out to, plug in a 2, plug in a 3. But that's the kind of the algebra part of the problem. let me know if you can't make sense of some of my stuff up here. I'd be happy to clear it up if I can. P3s, any others you want to look at? Yes. 113. Hey, we have a new one. Okay. All right, 113. The problem states, let's see, I got to find it here first. Think about it. Must the sum of two second-degree polynomials be a second-degree polynomial? If not, give an example. So if you add two second-degree polynomials, do you have to get a second-degree polynomial? That's the question. Well, if I just make some up, like I was just thinking about a different kind of second degree where you have like an xy. Yeah. Shouldn't affect it at all. So anyway, A, B, C, D, E, F are just constant numbers. So I have here two generic second degree polynomials. What happens when you add them? Well, you add the like terms. What's going to happen when you add ax squared plus dx squared? You're going to get a plus d times x squared, right? Does the degree ever change when you do that? No. And so, in answer to the question, must the sum of two second-degree polynomials be a second-degree polynomial? I would say yes. They do. Did they give an example?
Yeah, like a negative and positive.
Oh, so if this was a negative a squared,
Yeah.
it could turn to be a lower degree. Yes, this is certainly correct. So you can't go up, but you could eliminate a term. Ah, very, very clever. So had D been a negative a, for example, then goodbye first term, and we'd have had a first degree left. So the answer is no. Thanks for telling me about that. Another one we should look at from P3. If not, I do want to get fairly early to dig into P4. It's loaded. It's got lots of stuff in it. It's not hard, but well, let's do that. I don't know. There are so many kinds of factoring and so many to keep in your head that this is a little bit more challenging. You've done it before. It just, I don't know, maybe it's been a little while since you've been doing it. Okay. So we got basically 4 learning objectives. How to remove common factors from polynomials, that's otherwise called factoring. How to factor special polynomial forms, those are a challenge. 3, factor trinomials as the product of 2 binomials. And 4, factor by grouping. 4 is kind of challenging again. Okay, so, well, let me just show you. This time I am actually referring to the website I have up there. I might have used slightly different titles than the book just did in those learning objectives. My first type on the website is called common monomial factoring. That is, if you have a whole bunch of terms, and if there's something that you can factor out in common between all of the terms, then that's the easiest kind of factoring to do. So for example, here I've got a 7, a 14, and a negative 35. Hopefully you can see that 7 is evenly divisible into all of those. So I could take out a 7 or a negative 7, Then there's an x squared y, an x cubed y squared, and an xy to the fourth. Notice there's at least one x in all of those, and there's at least one y in all of those. So that tells me that I could factor out a 7xy. Usually in math books that's referred to as a common monomial factor. It's the first kind of factoring you learn. It's the easiest kind. Is it important to take out the greatest common factor when you're factoring? You know, like, should I have made sure that 7 really was the highest number I could take? Yeah. If you don't take it out, you wind up having to take it out later. So you try to find the greatest factor common to all. Okay. Now, this is a stinker, what I have listed in second position. The book calls it factoring by grouping. I, on my website, call it common binomial. Let's see. I think what I'm going to do is just start a new page and just, these are stinkers to make up. So let me see. I'll tell you what I'm going to do. I think for our examples, I'm going to try to find some evens on the assignment. Yeah, how about number 50? We'll take that as an example here. And then we'll come back here. Number 50 on the assignment says negative 3x to the fifth minus 3x squared plus 6x plus 9. This may or may not work, but I'm going to try it. Okay. Frequently, this kind of factoring will have 4 terms, as you notice we do here. And instead of saying, oh my goodness, I have no idea what to do, I call it divide and conquer. Divide it into 2 chunks, just leave them where they are, and just think of it like this, in these 2 pieces. And then, one piece at a time, can you factor each piece? So for example, piece 1. I could what? I can definitely factor a negative 3 out of there. In fact, can't I take a negative 3x squared out of there? Okay. What does that leave me with for piece 1? An x cubed and a minus 1. Okay. A plus 1 because I took a negative out. Thank you. Okay. And then in the second part, what can I do with that? Well, I could take out a 3. That's about it, right? Okay, it didn't help a whole lot in this case, because what you're hoping for at this stage of the game, and I obviously didn't pick a good example, even though we factored parts of this, we have failed in factoring this polynomial, because what you're hoping for is that what will come out in parentheses is a common factor, and if it is, then you can go on and actually factor it. Why is this not factored? Because of the crazy plus sign right there. This is not one thing multiplied by another. So my technique didn't work on that. And by the way, what were the directions there? Now, I did it right. It's just not an example of the kind of problem I was showing you. So there we go. I should be in the 65 to 72 range if I'd have looked a little more careful. So let's take, let's take 72. Yes?
For number 50, is it possible that you could have looked at the whole thing and just factored a 3 out of the whole thing instead of dividing it?
I could have, yes. Yes, I certainly could have. I was hoping for this kind of factoring, and that's why I did it the goofy way that I did. But absolutely, you can do that. Good question. So let's take 72, I'm sorry, is the kind I really wanted here. So what do we have here? 8x to the 5th. See if I can find enough space to put this stuff all up here. Okay, 8x to the 5th. Minus 6x squared. plus 12x cubed minus 9. Okay, now this time, in answer to your question, Michelle, this time I'm out of luck because I have 8, 6, 12, and 9. There just are no common factors there, so, but that's a good, you're right, you should look for that. So this time I'm going to use the old divide and conquer, and I think you're going to like the result here. So what can I do with this first group? Well, the greatest number I could take out is a 2. And I could take an x squared out, yeah. What's left when I do that? Four x cubed. All right, now part 2, what can I do as a kind of a separate problem? What can I do with that? I could take a 3 out. Okay, now, this is what I was talking about. We really got lucky, because look at what is in parentheses twice. The same thing. Okay, now, even though I haven't factored it up until now, I mean, I used factoring to get where I am, but because of this is not factored yet. This is an addition problem. But now comes the great next step. 4x cubed minus 3 appears twice, so I can remove that chubby common factor, 4x cubed minus 3, and when I take it out of this, what's remaining in the first part? A 2x squared, and what's remaining in the second part? A plus 3. And now I actually have it factored. Here we actually have one thing times another, and you just go back and check it and it'll work. So it's kind of like, all right, try divide. If you have 4 terms, try divide and conquer. Take out what you can, and keep your eyes peeled for a common binomial, or I've been calling it chubby, a common chubby factor. Take out the chubby factor, and what's remaining. And this is 72 is an excellent example of common binomial factoring, or factoring by grouping. Let's do another one of those, try to get a feel for this. How about 70? Let's see if that one works. Okay, we have x to the 5th plus 2x cubed. By the way, do you think it's okay? Do you think it would have been okay in 72 if I'd have taken this 4-term polynomial and rewritten the terms in a different order? It's certainly legal to. You can add and subtract in any order you want, right? Turns out usually you don't need to, but it's certainly okay if you feel like you could attack the problem better that way. Plus x squared plus 2. Okay, divide and conquer, part 1. We can certainly take out what, an x cubed? And that leaves us with? It's supposed to be a 2. And then I could just think of it as, I called it 1 times x squared plus 2, because is there anything I can really take out of x squared? I can't factor x squared plus 2. But look at it. I have a common binomial factor. I can now remove the chubby factor, x squared plus 2. And what's remaining? X cubed plus 1. And now we really did factor it. To me, this is one of the, harder kinds of factoring to catch on to. But it's not, again, let me just go back and hit some big things. When you have 4 terms, this is a candidate. Sure enough, these were all 4-term polynomials. Try divide and conquer. Divide it into 2 chunks, factor each chunk as good as you can, and then observe. Did you wind up with any common factors? If so, step 1, smile. Step 2, remove common factor. Continue smiling. Well, you can drop the smiling part, but it's good news because it means you've arrived at I don't know. Do we need to do one more of those, or are we pretty good with that? I think we're okay. Were you saying I should do another one? No? Okay. So now, back where we were. So that was the second kind. Now, number 3 on my list on the website is the difference of two squares. The difference of two squares. Again, I'm going to start a new page, and I'm going to insert. Here I'm just going to make up a bunch of them. Okay, so like, literally, each term has to be a square, and there has to be a subtraction sign. That's what we mean by the difference of two squares. So clearly, a squared minus b squared fits the bill, right? Whenever you have that, there's always a really cool way to factor that. I'm going to show it to you in kind of a weird way. Take the square root of the first term, put that in the beginning of each. Take the square root of the last term, put that at the end of each, and then just make one a plus and one a minus. So we have a special name for these two guys. Notice they're exactly the same, except one has a plus and one has a minus. Those are called conjugates. I think you need to know that word because it's going to come up in a number of contexts throughout the year. So when they're both binomials, and one's exactly like the other, except that one has a plus and one has a minus, they're called conjugates. And the special thing happens when you multiply conjugates. You get no middle term. And you just get this difference of two squares thing. Here, let's try another one.